Right, so the first thing we're going to do today is to take a look at the homework assignment because you will need the solution of this homework assignment to get started with the next homework assignment. So the next homework assignment is almost there, it's not quite there yet. I'm just looking at a mic here. It doesn't seem to be recording as usual. Okay, maybe it's just how I turn the mic. It's now facing me a little bit better and can capture my voice better. There we go. All right. So we go back to the CNF homework assignment first. There's a new homework assignment to use a proof by contradiction and also resolution. But we'll go back to this one first. So what we want to do is to convert this expression into a CNF, into a single CNF. And the way to do it, I'm going to scroll this up a little bit so I can fit my notepad right underneath. Because this is a notepad, I'm going to use the simplified notation where multiplication is conjunction and addition is disjunction. Okay, so we'll start with a negation of PQ. P and Q implies R, and then or Q and the negation of S plus T, which is S or T. Okay, so this is where we start off with. And you can start on both sides too. You can apply the Morgan's law to the right hand side and apply the definition of implication to the right hand side. So I'll do both at the same time. So it becomes not PQ or R. Okay, and if you want to make sure that you got the precedence correct, you can always add additional parentheses. And then the other side is Q and then this is the negation of S or T, which means we can apply the Morgan's law. So when you apply the Morgan's law, it becomes not S, not T. So just like that. And then when you get back to the first one, you can apply the Morgan's law here, but you will realize that if you apply the Morgan's law here, it will be countered or by the outer De Morgan's law. So you can apply the outer De Morgan's law first, then the entire thing is easier to deal with. So that's what I would do, is to apply the outer De Morgan's law, which end up with not PQ and then not R here. And then the other side is just Q not S not T. And double negation obviously cancels out. So now this becomes PQR on one side, and the other side becomes Q not S not T.
Yeah, no.
Huh? Oh, not R. Thank you. There we go. And at this point, you can apply. I forgot about the plus in between. So now you can apply distribution. So in this case, distribution is just expanding the whole thing out. Okay. So it becomes PQ, P or Q, and P or not S. And P or not T, and then you have Q, so you have Q or Q, which is Q itself, and Q or not S, and Q or not T. If you want to simplify these terms, like right here, that's fine too, but I just like to spell out everything first. So not R or Q, and not R or not S, and not R or not T. So the most obvious simplification we can do here is the Q or Q becomes Q. So I'm just going to copy and paste. So once you simplify this not Q or Q to be just Q by itself, then you will also simplify these guys out. These three will be gone. Because when you have Q inside a conjunction, anything that is Q or whatever will go away. Yep.
And here too.
And the P or Q, the first one, correct, yep. So you can, huh?
You don't need to, right?
You don't need to.
Yeah.
Yeah, if you get to this point here, even without simplifying the Q or Q, it is already a CNF. So you can turn it in and get full credit for that. Okay? But I'm gonna go the extra steps here just to simplify as much as we can. So and then we'll just copy and paste this here. Anything that contains OR2 or Q or can be now gone. So we'll take out this, take out this, take out this, and then the rest we cannot simplify any further. So it can simplify to something that has 5 terms. Good. Yep, go ahead. You can do it in different ways. I mean, this is just the way I do it. You can go through, you can use other ways to get to the same point. There's no one single correct way to do it. Yep.
So that's considered CNF? That's considered CNF?
That is CNF.
Even though Q isn't a disjunction?
No, you can always do this.
Yeah.
Yep. Is that okay? Why the simplification process? You mean why we could get rid of these terms? Right. I think that was talked about last time. Yeah. Yeah, so basically, you're talking about a truth table like this. So you want to complete this truth table and look at what is A and A or B, the result of that, and how it is actually the same as A. So once you look at the truth table, it will be pretty clear. So, okay. Yes. All right. So we can see how going through okay. But you don't have to do it. This simplification is not required to get full credit for this homework assignment. As long as you can expand it out into this, it will still be good. So this is a full credit submission. Yep. The fourth step here? Well, there's no negation on the outside of a conjunction or disjunction, so you can't really quite apply De Morgan's law. Now, sometimes you can apply De Morgan's law if you just inject negation, but you cannot inject just a single negation. You have to inject like double negation here, which I don't see why you would want to do that because it doesn't help. Okay. Any other questions? Now you can also reverse De Morgan's law. You can take a look at these two and say that is really just the negation of S or T, but that's how we started off with. Any other questions about this one? Okay. So the answer is this. If your answer is not the same, you can always use my solution as the starting point of the next homework assignment. So I'm going to do a copy here. Oops, clicked on the wrong link. So we'll go to the next homework assignment, which is proof by contradiction combined with resolution. It's not entirely done yet because I want to paste my solution into here first so that everybody has the same starting point. Okay. So there we go. Now that we have the CNF and the CNF assignment, so I'm going to put it here. I'm just going to use this notation, which is a lot easier to type, okay? Unless you guys really insist that I use the wedge or the U and the proper negation. Yeah, that takes a lot longer to type. This is like easy. Okay. So the next thing we want to do is to prove theorems, okay? Either proof or disproof. Okay, you have to tell me whether these things are theorems or not. So I'm going to give you, something to begin with on the fly here. So I'm going to have to mentally do the math and then present the theorem that I want you to prove. Some of you guys will say, let's just prove that Q is true. Because that would be pretty easy. But we're not going to do that. Still be pretty easy, but we'll do it. This one is just going to be S implies T, okay? Let's make it a little bit more fun. There we go. So S implies T or Q, okay? And we'll make the next one S implies T and Q. That's it. So here are your two theorems that you have to either prove or disprove. With one is S implies T or Q. Using resolution. So you have to use resolution to prove it by contradiction. So do you guys remember how to apply resolution in proving equivalence? Okay, we'll take a look at it. That's just, easier version. U is drink is fine. Plain water. So if you guys look at this water, it's only transparent liquid. Who you know who knows what it is, right? It could be vodka for all we know. Trust me, if it's vodka, I wouldn't be able to talk in any way. Yeah, that would make it a very interesting test. Yes. All right, so that's your homework assignment, and we want to go back and talk about proof by contradiction and resolution. And I thought about this whole thing, earlier today, like 4 a.m. And there are a few things that I want to kind of emphasize as well, but we'll talk about it when we get to that point. All right, so we are going to almost at the end here. So this is proof by contradiction. So once again, I just want to start with the rationale of these things. So the first rationale is to use resolution. Resolution is because of this implication being always true. So let me point out one more time. This implication, this entire expression, is guaranteed to be true all the time. What is that saying? Well, what all that is saying is if you know this is true, and also this is true, then this implication is always true. But with an implication, when the first part is true, there's only one condition that can make the entire implication true, which is the second part also has to be true. Okay? And that is why we can use it as the basis of the resolution inference. So the inference looks exactly the same thing, or almost exactly the same. great, because this means, you give me any theorem to prove, I first have to convert what is known to be true into one single CNF, and then we use proof by contradiction. So proof by contradiction is the next ingredient here. So when you go to proof by contradiction, it is right here. So proof by contradiction has its own proof, which is a direct proof. It will be kind of difficult to prove proof by contradiction using proof by contradiction. But it's a direct proof. So the direct proof relies on a corollary, which is a smaller theorem, which means which is basically saying this. It is saying that this implication is always true. In other words, if you tell me that P implies Q is true, then I can say, give me any R. Okay, it doesn't even matter what R is. Give me any R, I can guarantee that P and R always implies Q and R. That is the corollary. So given that corollary, we can now say, oh, okay, psi implies phi implies this thing here. Okay, so this implication, which is going from the first line to the second line up to here, is due to the corollary that we just talked about. Okay, but then you go, oh, of all the things that you can add, after the conjunction, you have to add not phi. Well, but there's no restriction up here. This R has no restriction. I can use any R I want to, right? So not phi can also be used here as long as I'm adding and not phi to both sides of the implication. But then you look at this whole thing and go like, but that's guaranteed to be false. So be it. Because what we ended up with is psi or not phi is going to imply false, guaranteed to be false. And that's our contradiction. But what is psi and what is phi in this case? Psi is the conjunction of everything that you know to be true already. So that would be your axioms, your other theorems, and whatnot. Okay, it can be huge, a gigantic CNF. Phi, on the other hand, is the theorem that you are attempting to prove. Okay, because you want to be able to establish that particular implication. In other words, if phi really is a theorem that can be implied from psi, then when you have a conjunction of psi and the negation of the theorem that you want to prove, then you're guaranteed to arrive to a contradiction, to something that is false, that cannot be true. Is that okay? Yep.
So in relation to our homework, we're trying to prove that the answer we got is the true part. So
yep. So.
Case.
Yep. So in relation to your homework, we look at one example here. Okay. So in this particular example, I use exactly the same symbol to mean exactly the same thing. So in this case, psi is something that is given to you to be true. Okay, don't ask me, but it is guaranteed that not P or the negation of R implies Q and P or T, this whole thing is guaranteed to be true. Okay, don't ask me why, it's given. But what I want to do is to say, what about this? If this is true, can we also guarantee that not T implies Q, it implies P is also true? That's the question. So what we do is we first express psi as a CNF, okay, and the exercise to turn this into a CNF was about, I illustrated the whole process to convert that part already, but we know that psi can be re-expressed as this particular CNF. So the next thing we need to do is to look at the negation of the theorem that we want to prove. So if phi is not T implies P, then the negation of that is just the negation of the theorem itself. And then you apply the definition of implication here. And then you apply De Morgan's law here. And then you ended up with not T or not P. Not T and not P, excuse me. Okay? And then what we want to do is to merge these two into one single super CNF, or the bigger CNF. And that CNF should always imply 0, because it is the conjunction of everything that you know to be true to begin with, and the negation of a theorem that you suspect is true. So if the theorem is in fact true, then this always should give you a contradiction or false. But in this case, it's not the case, because this part here, okay, there we go. So this part, the first part here is from psi, which is the things that are given to be true. The second part here is the negation of the theorem, but we cannot even do a single step of resolution here. There's nothing to resolve. Because in order for resolution to work, one part of one disjunction needs to have a variable where another disjunction needs to have the negation of the same variable. I cannot find a way to do this resolution here. If you cannot do a resolution, you cannot conclude to false or zero, that means the theorem that you're trying to prove is not a theorem. So in this case, we come to that conclusion right away and say that, oh, that thing is not a theorem. This phi is not guaranteed by psi. Yep.
Couldn't we simplify that?
Simplify.
Not P.
Oh yeah, totally. Yeah, because you can simplify, but the whole point is there's no resolution. You cannot resolve.
What do you mean there's no resolution?
I cannot apply resolution here.
And like, what's that mean?
That's what we mean earlier, up here.
There's no negation.
Like you can't turn it
Oh.
into one?
I cannot turn it into a zero. I'm not interested to one, I'm interested in zero. Because that's the whole idea of that's the contradiction part of proof by contradiction. Okay? So that means, it's not very exciting because, that theorem turned out not to be a theorem. But it is important to understand when you can come to the conclusion that it is not a theorem is when you cannot resolve to zero. Okay? If the conjunction between what is given to you to be true and the negation of the theorem that you're trying to prove, if that super CNF cannot resolve to zero, then the theorem is not a theorem. Or what you suspect was a theorem is not a theorem. Does that mean the theorem is always false? No, it just simply means it is not implied by what is given to be true. Sometimes it's true, other times it's not, but it's not guaranteed. Is that okay so far? All right. So the next one is phi prime. Okay, so this time I said, okay, maybe this is a theorem. Maybe what we're given with, which is this part here, guarantees that P implies not Q. Is that okay? And how do we know? Well, first of all, we want to say, okay, let's take the negation of phi prime. The negation of phi prime is the negation of P implies not Q. I applied the definition of implication first, and then we perform the De Morgan's law on the outside, and so we ended up with P and Q, which is a CNF. Okay, if it doesn't look like a CNF, you can always say it's P or false in parentheses, and then Q or false in parentheses. That makes it a true disjunction. So now we say, okay, let's combine the negation of the theorem that we are trying to prove with everything that is known to be true, which is in psi. So now we have this quote unquote super CNF, and in this particular super CNF, I forgot a backslash before the phi, and that's why I spelled out as phi, but it is still phi. So in this case, you can look at this and go like, oh, we got plenty of stuff to resolve. Now remember, in resolution, you want to do it one step at a time. Only resolve one variable at a time. So there are different ways to do this, in different order. In this case, I can first resolve the not P with the P here. Okay? Okay, let me use my text editor here so I can show you exactly a little bit more in detail here. Okay, so we have not P or R, and not P or not Q, and P. Now remember, the P is really P or false, and then the Q is always Q or false. Is that okay? Okay, so resolution means I need one disjunction to have a variable non-negated, and I want another disjunction to have the negated version of the same variable. This time we got choices, right? If I want a not so productive resolution, I can say, hey, I can resolve between this guy and this guy. Yep.
Are you supposed to have that not Q1 semicolon?
What?
Have P, Q, and
You mean
not
here?
Q? Yeah.
That's after one resolution.
Okay.
So I'm showing you how to do resolution here.
Yeah.
Okay, so if I want to do a resolution, I'm going to use a very crude way to indicate which two I'm resolving. Okay, this is an underline, and this is another underline here. These two expressions can resolve because one has p, which is the non-negated variable, and the other one has not p, which is the negation of the same variable. Okay, and now we can resolve. Resolution means I can now create a new term. So I'm going to put a new term here, which is ended with the rest, okay? Because the new term actually doesn't add any new information, because everything is already implied by what we have here. We're just having a different view of this. So the new term is going to be the concatenation between the two underlined expressions, except the variable itself is taken out, and as is the negation of that thing. So now this becomes R or 0. The R comes from the first expression, and then the or 0 comes from the second expression. Is that okay?
That's resolution, right?
Huh? That's resolution. That's one step of resolution that is useless in this case, but I'm using it as an example. Okay? So if this is a resolution, I can resolve it one more time and say, hey, I can look at this term. And by the way, if you have already used an expression for resolution, you can use it again. There's no rule saying that you cannot use the same expression or the same disjunction to resolve multiple times. So this time I'm using P or 0 as one of the expression. I'm using not P or not Q as the other term for resolution. And to be very clear, this not P versus this P is what allows this particular resolution. So I'm adding another term here, okay? Because after this resolution, I get not Q or 0. Because I took out the P or not P, so that one is gone, but I ended up with not P or 0. Is that okay? It's a concatenation. You get rid of the variable where it is negated on one side and non-negated on the other side. Whatever is left over, just concatenate. Becomes its own expression. And whatever expression you come up with can also be used for resolution purposes. So this time I'm going to use this one and resolve it with this one over here. Okay. Okay. So they are clearly resolvable because one has Q and the other one has not Q, right? So technically speaking, if you do it syntactically, then you end up with 0 or 0. Yep.
So what if the theorem you give just gives you back the exact same answer?
Then if you have no further resolution to be performed, if you cannot get to contradiction, which is what we have now, then the proposed theorem is not a theorem.
So
You hit a dead end.
Okay.
Yep.
So even if it just goes all the way back, like you didn't prove anything part of it, it also just goes back out to the original theorem, the original proof.
Right. Yep. So you have to arrive to the contradiction in order to terminate. Or the other way to terminate is I cannot have any further resolution to come up with terms that is not already here.
Okay.
Yep.
On the third line, there's a T that appears. I don't know where it comes from.
On the third line, we have a.
In your notes.
Oh, in my notes.
Yeah.
Oh yeah, not
Q
Q
or
or
Oh,
T.
that's because I made that change earlier in the class. I corrected this in the earlier class, but I forgot to fix that row. So just kind of imagine that this one is not here.
Is it supposed to be 0?
That was the other one we fixed before.
Well, that's before we fixed the other thing.
I think that was the example that we fixed last time.
Yeah. But I forgot to fix this, one part of it. Okay, but getting back to this example, are we okay so far? But because we can arrive to false or false, which is false itself, And this is inside the big conjunction. Remember, every time we add the result of resolution, we are adding to the conjunction itself. So when you have a false and blah, 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 I don't even care what the blah, 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 blah is, because false and anything is false. So now this entire thing is false. So basically at this point we have proven that psi and not phi prime is false. Well, based on proof by contradiction, this means that phi prime is actually a theorem.
You erased your resolution that led you to zero then? There's no zero to zero.
There's no, oh, okay.
Yeah.
There we go.
Discontinuity.
But that's why video recording is good, because you can see it was there, now it's gone.
Yeah.
Just roll back a little bit, it's there again.
Yeah.
So are we good so far? I know it's kind of complicated because it takes several concepts and it has to combine all of those concepts in order to work. Go ahead, and then you.
The first step was to negate the original question.
Okay, so you have to be more clear. Okay, the question is, I give you something that is known to be true to begin with. Do not negate that.
No.
And then I say, I suspect this is a theorem. Negate that.
Yeah, okay.
Okay, and then turn both into a CNF. Everything that you know to be true, turn that into its own CNF. The negated version of the theorem that you want to prove, turn that into a CNF. Plug those two together to have a quote-unquote super CNF. Apply resolution until you hit one of the two conditions. One, you get false, like what I have here. Or two, you cannot apply resolution and you do not have false. Either way you stop. If you end up with a false here, that means the theorem is true. Okay, it is actually a theorem. And then if you get to a point where you cannot resolve any further, but you cannot get to contradiction, that means whatever you suspect was a theorem is not a theorem. Is that okay?
So being false means it's true because it's supposed to be false.
Having false means the negated theorem leads to a contradiction, and therefore the theorem is true. And it all has to do with the proof that we showed a little bit earlier here. That's the proof of proof by contradiction and how it works. All right. So are we okay on all of these ingredients, you know, how they work together? Yep.
I'm still a little confused on the part where when we back on the text document, we had the r plus 0, like the parts that we found using resolution. Are those all like are they all separated by conjunction? Or?
Yeah, okay. These are all, you know, this is one gigantic conjunction. So basically,
the entire problem is.
Yep.
Oh,
so
okay.
at the end, we ended up with a conjunction that has not P or R and not P or not Q and P or false and Q or false and R or false and not Q or false and false or false.
Okay.
That is our actual conjunction. But it kind of makes sense because when you look at, okay, so let me scroll back to the part that shows, you know, the logic basis of resolution first, okay? So when you look at this, okay, what is that saying? It says, you know, if you know this is true and you know this is true, then this has to be true. That's what it's saying, right? Okay, because that implication is always true. So when we switch back to the note here, we are basically saying if we know this is true and we know this is true, which we do, because these are given to be true, right? Then we also know this to be true because that's the result of resolution. Well, since they're all true together, that means, you know, I can add R or false to the original conjunction without changing the truthfulness of the original conjunction. Let me say that one more time. This is known to be true. This is also quote unquote known to be true because it comes from the proposed theorem, the negated version of that, right? So if we know these two are known to be true, then this has to be true as well. Well, since they are all true at the same time, they can be connected by a conjunction. And that has to do with the property of resolution itself. If this is true and this is true, then this has to be true. Well, if that has to be true and the other two is true, then having a conjunction of all three is not a problem, because they are all true to begin with. Yep.
So this process, this whole process, it uses the resolution and the proof by contradiction evidence.
Yep. But it also depends on the CNF of the first homework assignment, because you have to express what is known to be true or what is given to be true as a CNF first. So the significance of the assignment that was due today is, given any Boolean expression, you can always turn it into a CNF.
So are you saying like the part that's highlighted, that's added to the expression, or that's substituted for the?
It is added to the expression.
Added to the expression.
It's added to the expression. So your conjunction gets longer and longer.
Okay.
Because all of these things, in this case, phi or rho is not adding any new information to the original conjunction, but at the same time, it is consistent with the original conjunction, and that's why you can attach it to the conjunction itself without changing the truthfulness of the conjunction. But we need that because whatever is the result of resolution itself can be used in further resolution. So that's why you have to attach it to the conjunction, because it can be used to resolve with something else later on. Is that okay? Yep.
So would it be wrong to get rid of the phi and not phi,
To get rid of the phi,
and replace it with the new implied statement?
you do not want to replace it, because this is the consequence of what is known to be true. So what is known to be true needs to be there, because you can get rid of this one without changing the meaning of the entire expression, but if you replace the original phi or psi with phi or rho, that will change the meaning of the original expression. The truth table would not be consistent anymore. Is that okay so far? Okay. All right. All right, so let me tell you what I thought about at 4 a.m. this morning. I just woke up at 4 a.m., and go like, I should talk about that. Okay. But I didn't have time to type it up. That's the problem. It was a little cold. I didn't want to get out. Okay, so let's say we're given with, 6 variables. Okay? So if we're given 6 variables, how many different conjunctions can we end up with? Okay, let's make it small. Nope, it has nothing to do with choosing in this case. So let's say we're given with 3. So we have P, Q, and R, okay? So you just kind of think about, okay, P by itself can be 1, Q by itself can be 1, R by itself can be 1, not P is 1, not Q is 1, not R is 1. Okay, so you guys get the idea, right? Okay, so now the question is, how many conjunctions can I make out of P, Q, and R? And each one would still be a disjunction that can be used in a CNF. That's the question. So the next ones, okay, I can give you a few more examples with the P or Q, P or R, and then we have Q or R, and then we have not P or Q, and so on. Okay, so when you look at this, the best way, the easiest way to look at this is you look up you make a table for yourself. So you look at P, Q, R as a table, but this is not a truth table because P can be absent, 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 and when P is absent, Q can be just Q itself, can be just Q itself, can be Q itself, can also be not Q. Okay, so we have not Q, not Q, not Q, when P is absent, Q is not negated, R can be missing, R can be itself, R can also be the negation. Yep.
So, it would be the amount of variables you have, do that, the first power plus, it's the second power plus all the way to how many variables you have, and then the end plus, how many variables you have, to the, times, plus, how many variables you have to the 2, so how many variables you have power, so 2 times.
You're making it more complicated than it needs to be. Because when in every single disjunction, okay, so this is the other way to look at this. In every single disjunction, there are 3 places. Blah, 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 or blah, 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 or blah, blah, blah. Okay? The first one has to do with P. The second one has to do with Q. The third one has to do with R. And they're independent, okay? Because these 3 variables are independent. Q can be absent, negated, or non-negated. Q can be the same thing, R can be the same thing. So it's 3 times 3 times 3, including false or false or false. Okay, so there are 81 ways to arrange 3 variables. Is that okay?
You said 3 times 3 times 3, 27.
Yeah, 3 times 3 times 3, which is 27.
So it's 3 to the 3.
Yep. So it is is 3 to the power of the number of variables. If you have 4 variables, then it'll be 81. So in our case, with 5 variables, technically speaking, there are 3 to the power of 5 many, ways to come up with these disjunctions. Is that okay? But why is that important? Remember the advantage of doing resolution and using proof by contradiction, as opposed to the open propositional logic thing where you can go in any direction you want, create any complicated, well-formed formula known to be true but totally worthless. How many ways can you generate well-formed formulae that are known to be true based on the earlier resolution rules? Infinite number. Okay? And you can go in the wrong direction forever and not know whether the theorem that you want to prove is a theorem or not. So in this case, okay, so I'm going to write it here. I didn't have time to actually put it in the notes here.
It's the number of variables to the number of variables plus 1 power?
It's okay. This is the equation. Given n variables, there are 3 to the power of n disjunctions.
So disjunctions can't have more than 3. They can't have 4 or 5, like 4s.
Yeah.
No, it's the other way around. It's 3 times 3 times 3 times 3 times 3 n times. Because each one is 3x. So when we have the next one, okay, so let's say we have S as, okay, this is a bad example because I have the same number. If you have P, Q, R, S, then you have 3 to the power of 4 ways of arranging your disjunctions, because each one can be missing, can be unasserted, non-negated, and also negated. So you got 3 options. So imagine each one can be a 0, can be the variable itself, can be the negated version of the variable. And that's why each slot has 3 options. But then when you look at the combination of these things, they are independent. Yep.
So when you said you had 3 variables, though, you said there was 81 combinations. That's 3 to the 4th power.
Right, I said it wrong.
Okay.
I was corrected. Somebody pointed out the way. That's 27 times 81.
Yes, I was like,
Yeah.
this is coming on confusing.
Yeah, it was corrected. I was corrected. Yep. So it's 3 to the power of n for n variables. But why is this useful? Why is this discussion useful? It's because no matter how you resolve, the result of the resolution has to be one of these 3 to the power of n possible ways of generating the disjunctions. Okay, so what is the big deal? That means your entire space of CNF is finite, as opposed to the general version of propositional logic the space of well-formed formulae is unlimited, it is infinite. Okay, why would that be useful? Well, if you think of it this way. In the case of CNF resolution and proof by contradiction, I'm giving you a haystack about this size, and I say the needle is in here, or maybe it's not. Find it. Okay, you go like, that's a chore, but I'll get it done, right? Because you know, in order to search through this kind of volume, it will take you, 5 seconds. So you just have to say, okay, this whole thing is about, I don't know, 100 times that volume. So it will take me 100 times 5 seconds, which is 500 seconds. I know I'll be done. Okay? In 500 seconds, if I do not find the needle is not there. It's not in the haystack. That's a conclusion you can make, right? If you find the needle, great. But if you can just conclude for sure and say the needle is not there, it's good too. As opposed to the other one, okay? If you look at propositional logic in general, using Boolean Boolean algebra as the basis, where you can have derivations to come up with new but useless well-formed formulae known to be true. I'm giving you a haystack that is infinitely large, and I say there might be a needle in this haystack. Go find it. How would you like that task? That's the difference. Okay. In this case, the haystack has a known size, and no matter how you apply resolution, the result of the resolution is one of these disjunctions. So that space is known to be only this big. Okay, there are only so many things you can do. There are only so many resolutions or so many inferences you can make within this space. At some point, you either come to contradiction, which is great, that's your needle, or you say, there's no more resolution possible. Okay, if I derive any further, I only get back what I already have. Then you can say the needle is not in the haystack. That's the important part. I knew about this part, long ago, but at 4 a.m. I kind of, it clicked, and I figured out how to explain it. But the haystack thing was just now. That's how my brain functions. Some people say erratically. But that's the important part, okay? This is why we want to do CNF, because CNF enables the application of resolution. But this is also why we want to use proof by contradiction, because proof by contradiction works well with resolution in order to come to the conclusion and go like, if we get to the, if we get to 0, that means we're good. Yep.
So these are WFF1s, right?
These are no, these are the WFFs.
Just regular WFF?
WFF, because every WFF inside the space, the ones that are known to be true are always connected by conjunctions. So the conjunction is implicit. So all of these are WFFs, where each one is a disjunction.
So we have finite WFFs in this case?
Yes.
Okay.
And that's why I said the space of your well-formed formulae is limited. You know exactly how big that space is. It cannot exceed that space. Which also means your exploration within that space can be done within a fixed amount of time. Now, is it a really good algorithm? Not really, because it is exponential to the number of variables that you're given with. But at the same time, it is still not infinite. You cannot come to a state where you keep expanding in the wrong direction and not know, cannot conclude whether the theorem is true or not. This way, this one you always conclude one way or another. So are we doing okay with this? Right. Okay. So we are pretty much done with propositional logic, resolution, proof by contradiction, and all those concepts at this point. So I can give you guys a choice of where you want to proceed. We can talk about Lotto, or we can talk about what else? I had that idea earlier this morning, then I forgot. Lotto is one which is related to probabilities and combinatorics, that sort of thing. And then the other one, I cannot remember. I just cannot remember.
Is that the one that has the pencil in it too?
Well, let's do Lotto then, okay? And I have the notes in Moodle, but not in Canvas yet. Okay, so I'm still moving my content from one server to the other server. So instead of using my notes, okay, I'm just gonna do this by demonstration, using a spreadsheet, possibly using my text document here. So the first thing is, should you buy Lotto? When do you want to buy Lotto? Okay, so we'll go to the Lotto website, and they have a lot of information too. So we want to look at California Lotto.
Oh, Lotto.
Lotto.
I didn't know you were saying lotto.
Oh, lottery.
Yeah.
Lottery. Okay, there we go. So they have many games, and we'll focus on a few, like really common ones. Giving back to the community, and there's this little girl with a stack of books. So what I really should do is to encourage you guys to play Lotto, because a part of that money goes back to education, quote unquote education. But this is a kind of like one of those paradox kind of thing, because with a educated population, no one's going to play Lotto. So the fact that somebody's playing Lotto means we need more education, and Lotto is used to fund more education. So how do you fund more education to make sure more people will play Lotto in the future? Don't tell them about Lotto, right? Don't tell them anything about probability and stuff like that. That's how we do it. Okay, so we'll pick a particular game. So we go to games, and there are many. Okay, we can pick Powerball. Okay, so the first thing you want to do is to understand the rules. Okay, so in the case of the Powerball, it tells you how to play. Okay, find a Powerball retailer, blah blah blah. Okay, pick 5 lucky numbers from 1 to 69, and one Powerball number from 1 to 26 on the Powerball pay slip. Now, what they did not tell you is the 5 quote-unquote lucky numbers cannot duplicate. Okay, you have to pick 5 distinct numbers, each one from 1 to 69. And then the ordering is also not important. Okay, if you pick the 5 numbers as 1, 2, 3, 4, 5, or 5, 4, 3, 2, 1, it's just as good. So the ordering does not matter within the balls that you pick as your lucky numbers. And then the Powerball, which is from 1 to 26, has absolutely nothing with the 5 lucky numbers. In other words, if you pick 1, 2, 3, 4, 5 as your lucky numbers, you can use 1 again as your Powerball number. That's fine. Okay, so the Powerball number has absolutely nothing to do with the lucky numbers that you picked earlier. Is that okay? All right. Okay. So how do we play this game? So you have to figure out how to win, and there are many ways to win too. You can skip step 4. I personally would. When you believe, the world opens up before you.
Believe.
That's okay, because the world will give you feedback so that you will stop believing in the future. It's called reality check. Okay, so you can win, based on these things. In other words, you can win the big jackpot if you have all 5 lucky numbers correct and also the Powerball correct. Or you can have just the 5 lucky numbers, the Powerball doesn't match. Or you can have 4 out of 5 of the lucky numbers matching, as well as the Powerball matching. You can have just 4 out of the 5 lucky numbers matching, but not the Powerball, and so on. And then the price level for each one is slightly different. Okay, well, not slightly, but they're different. Okay, and the odds is expressed in 1 in, which also means if you want to look at the probability, it is 1 over that number. Now the reason why they express odds in 1 in blah 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 instead of giving you a a number that represents the probability is there are many people who cannot read decimal numbers. They do not understand 0.000000 something 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 is a very slight chance. Okay. Now I'm not saying this with with contempt or anything like that. I'm speaking of this as reality. People just some people do not understand that aspect of decimal numbers. So they have to express it in terms where most people can understand. Go like, wow, okay, so 292 million. Okay, that's a pretty big number. Okay, I probably will not win jackpot. So that people understand the chances of winning jackpot. So are we okay so far in terms of the rules of the game? Okay. Now the second part of playing lotto is people can buy tickets of exactly the same numbers. Okay. In other words, first of all, let's figure out how many possible unique tickets do we have here. And to do that, the best way is to use a spreadsheet. Spreadsheets are very useful because they're really just a big visual calculator. So they're really handy for a lot of things. Okay. All right, so we'll use this spreadsheet to calculate, what is the total number of unique lotto tickets that are possible. Is that okay? All right? Okay. All right. So you just have to kind of imagine the process where you are choosing your lucky numbers. Okay? So according to, oops, not this one. According to how to play, the lucky numbers range from 1 to 69, which means the first lucky number, oops, I keep using the wrong way to do it. Okay, make it a new window. There we go. So you have 69 numbers to choose from as your first lucky number. Is that making any sense? But once you have chosen your first lucky number, how many choices do you have left for your second lucky number? 68, which is this number minus 1. Okay, pretty easy. And then the next one is going to be 67. Okay. And then 66. And then finally 65. Okay. And plus the super ball, or how is it called?
26.
Super Powerball. There you go. So Powerball is 1 to 26, but that has nothing to do with the things that you have chosen already. So when you multiply these numbers together, is that the number of unique tickets you can get? But remember, order does not matter. Okay? When you look at these numbers, does it count 1, 2, 3, 4, 5, and 5, 4, 3 to 1, and 1, 3, 5, 4, 2, all separately?
No, because order doesn't count.
It does, right?
Order does count?
It does count all of those
Oh,
as
there it
unique
is.
tickets, which is not what we want. Right? Because when you look at this one, it says, okay, with the first number, you can choose a 1 to 69. If you choose 1, then the second number can be 2 to 69. If you choose 1 and 2 for the first two, and then you can choose 3 to 69. On the other hand, if I choose 5 first, then you can choose 1 to 4 and then 6 to 69 as the second number. In other words, it doesn't account for the fact that 1, 2, 3, 4, 5, 5, 4, 3 to 1, 1, 3, 5, 4, 2, 2, 4, 1, 3, 5, they're all considered the same. Okay, so we have a good starting point. Okay, so the good starting point here is multiply these numbers together. It doesn't give you the number of tickets yet, but it does give you a number to begin with, which is really huge. So now we look at this number and say, okay, that's way bigger than what it should be, but how do we shrink this number and account for the quote-unquote duplicates, where, oh, there's 1, 2, 3, 4, 5, 5, 4, 3 to 1, and so on and so forth. Well, if you think about it, it is a question of, if I give you 5 things, 5 unique things in a box, how many ways can you arrange those 5 things? Right? Because 1, 2, 3, 4, 5 is one way. 1, 2, 3, 5, 4 is another way. 1, 2, 4, 3, 5 is one way. 1, 2, 4, 5, 3 is another way, and so on. So the question now is, okay, with 5 things in the box, how many ways can you arrange those things?
Would you divide it by
5 factorial.
5 factorial, very good. Okay, so with 5 things in the box, there are 5 factorial ways to arrange it. So I've just kind of spelled it out here. So equals FACT for factorial 5. When you divide these two numbers, then you get the unique numbers, right? Because now ordering does not matter because you have accounted for the 120 ways to generate the same. Out of 5 things, you can now generate different things in different order. So if you divide this number by this number, that's the number of things you have. But then we still have to multiply by 26, okay? So I will say this is the number of permutation, okay? So we'll re-examine these terms later. This is the number of combination. So the number of combination for those 5 lucky numbers is this number. We have to remember to multiply that to 126. So the number of unique Powerball tickets. Okay, change this a little bit. Is going to be this number times this number here, and that looks. Does that look familiar to you?
Yeah.
Okay, 1, 2, yep, 292 million and blah, blah, blah. So this is the unique number of tickets, which is about the same as the population of the United States, okay, about 300 million or so, okay. And whenever we have a big jackpot, what happens?
Multiple winners.
There are multiple winners. How can we have multiple winners? Because there are more people buying tickets than there are unique tickets, right? Okay, so it becomes very difficult to anticipate whether it's worth it to buy a ticket or not. Even knowing the jackpot, it is now very difficult to basically say, is it worth to buy? Is it worth my money to buy tickets in lotto? Okay, I'll give you one really extreme scenario. So let's just say that we don't have tax consequences. Okay, so the money that you win from playing lotto is not taxable. Okay, and let's just say the bank is ready to loan you a lot of money. And let's also say that for each possible ticket, only one person can buy it. And on top of that, you are the first one in line in 7-Eleven. And you say, I want to buy all the possible tickets, so nobody else can buy any ticket today. Is that okay? Based on all of those assumptions. And let's just say the jackpot is exactly that amount of money, and it costs $1 per lotto ticket. What do you think? It will break even, right? You go to the bank before you go to 7-Eleven, and you borrow exactly that amount of money, to $292,201,338. The bank says, what do you want to use this money for? I want to buy lotto tickets. Lotto. Bank says, okay, fine. Here's your pile of money, okay, or your cashier's check or whatever. You take it to 7-Eleven, okay, you're the first one in line. Somebody held the line for you, held up your position for you. You walk in, you just buy all the tickets, okay? Remember, we changed the rules, okay? Once you buy a ticket, nobody can buy the same ticket anymore. And then you walk in and go buy, I'll buy all possible tickets. All 292 million and whatnot, okay? So you end up with a big pile of tickets, right? Of course, you drove to the 7-Eleven using a U-Haul truck because you end up with 292 million tickets. And guess what? You're guaranteed to win jackpot. Woohoo! Okay? Actually, you win a little bit more than that. I'll explain that later. Okay? So that's good, right? But you're also guaranteed to win the other prizes too, because when you look at the rules of this game, you also get to win all of these other ones, guaranteed, because you bought every single ticket. But the prize money is not quite as good as jackpot, so you do end up with some change in your pocket, okay? And you take the $292,201,338 back to the bank, and you return it to the bank and go like, okay, thank you very much, I'm done. On the same day, right? Yep.
And don't forget to write off all your dues and tickets and taxes.
Ah, that's right. So you actually ended up paying less tax money in that year. Reporting as loss, right? Okay.
You can report lottery losses.
No.
You can report lottery casino losses.
You can?
Yeah. Lottery because the money goes directly to schools.
Just for the state.
So it's almost like a donation at that point.
Not
Transfer
for
money.
federal.
I know you can.
So, but anyway, so given the jackpot, given all of these unreasonable rules, okay, and given that you can borrow money from the bank with no interest for a very short amount of time and stuff like that, yes, okay, things are predictable and you can probably decide when to buy a ticket and when not to buy tickets. Yep.
So if I have the 4 out of 5 Powerball, do I get all the? So there are. Let's say I have the 4 out of 5 with the Powerball number. Then I have 69 tickets like that, right?
There are.
Because my.
No, there are more than 69 tickets. 4 out of 5 Powerball.
Yeah, so I get all that
there are
money.
more. Yep, because you have all the
For each
tickets.
ticket?
Remember, you got every single ticket
Oh
possible,
my
right?
gosh.
Yeah.
That's almost more money than those ones.
Yeah, yep. You get some spare change in your pocket, but not in the order of $300 million. You win the other ones. You win all of the other smaller prizes as net gain because you have to pay back the bank for the money that you borrow to buy
But I
those
win
many
the smaller
tickets.
prizes multiple times, right?
Yep, exactly. There are many. Yep, you win those multiple times, but I don't know how much they pay back for the smaller prizes. Yep, go ahead.
No, I was gonna just ask that, and you said you don't know, like, the difference.
Oh yeah, I don't know exactly. Maybe it will tell here. Prize money. There we go. Okay, so I don't know how they determine the prize money for the 5 but not Powerball. Whether are they fixed or not? Does anyone know? I know the lower ones. Just winning the Powerball for $3. I think those are fixed. Having one lucky number matching and the Powerball is $5, I think those are fixed, but I'm not sure about the higher ones. So to answer your question, if that is the scenario that we were playing with, then you have 5. Well, these are winning tickets, so, but you have all the winning tickets, by the way, right? Because you bought every single ticket that's possible. So to have 5 lucky numbers but not the Powerball, how many tickets are like that? Okay, here's a quick question. There are 26 numbers to pick from for the Powerball. Okay, so if you're looking at the ones that have all the lucky numbers matching but not the Powerball, how many tickets will win you $925,000, which is a pretty good chunk of money for one ticket? No. 26. No. 25. Okay, because out of the 26 possible ones, one is the jackpot, which doesn't count for the second prize. So there are 25 of those, and 25 times almost $1 million is a good chunk of money. Not compared to 300 million, but it's still a good chunk of money. I'll take it. Okay. All right. So given all of those conditions, yes, we know how to play the lottery game. But what is unknown that makes lottery so unpredictable and usually unprofitable is they do issue tickets multiple times. The same numbers, the same lucky numbers, and the same Powerball number. There may be multiple tickets with those things, and you have no idea how many duplicates we have. So as a result, even if you know the tax rate, even if you know that you can borrow money and you know the chances and stuff like that, the one thing you cannot model is how many tickets are going to be sold. Because when the jackpot goes beyond $300 or $400 million, guess what? A lot of people will think like you and go like, okay, it's worth it, chancing it, and I'll buy tickets. But you have no idea, at least I don't know of a particular model or a particular statistical model to model how many people will buy tickets given a certain amount of jackpot. So as a result, usually it is not worth your money to buy lotto tickets. Okay, I'm going to end this class, and we have 2 minutes left, with a comment on, so how come people are still playing lottery? And a lot of people who play lottery are not, it's not because they don't understand probability and stuff like that. It's because of the belief that, yes, statistics and probability applies, but only to other people. I'm the lucky one when statistics does not apply. If you ask gamblers, that's exactly their mentality. It's like everybody else is not as lucky as me, so that's why I'm gonna go to the casino because I'm gonna win. Everybody else is gonna lose. All right, I'll see you guys on Wednesday.
Yes, losing tickets, any kind of lottery or casino losses are taxable.